So last time, if you remember, we defined something called the statistics exponential, and there we have a term like phi r z to the power r for u1, and as of now, I mean that point, it may seem that okay, z to the power 1 is the the character for the u1. Then I wrote down as like chi to the power r or something like that. But certainly, as Siddhartha Kayatri pointed out, that is not translated for the non-abelian theory. That actually the character is basically, you can think as a function of z, and that character individual elements will be to the power r. So let me write down the generic character here. So statistic exponential phi of r as exponentially r equal to 1 to infinity r chi r j r divided by r. Okay, so that is the definition of a statistics. Here I am assuming that phi are basically the bosonic fields. Okay, and when I am saying bosonic field, that means we have a notion of, for example, x or the f mu nu and also the phi. So all integer spin including the 0, we will define the character in this statistics in this particular form. R is the representations, okay, and zj tells you how many torus coordinates will be there. So for example, if I have a SU2, okay, I only have a 1, you have a SU3, then it will be 2 and so on. So I will tell you what is the counting of that thing, and this just as R here, and yeah, so this is all. If you expand that, it will give you all possible tensor products for these representations, but this is only for a single field. Now, while constructing the statistics, also it takes care about the spin information of the fields. That means if they are fermionic in nature, then the fermionic fields are anti-commuting in nature, right? So when you construct the Lagrangian, that information also should be propagated, and that is being captured in the statistics as following. So you define the statistics for fermion field as exponential r equal to 1 to infinity minus 1 to the power r plus 1 psi r let's say r by r. Okay, so there is the additional factor of minus 1 to the power r plus 1, and that you can see that because of the to capture the anti-commuting nature of the fermion fields. Yeah. 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 So basically, so it's not like I am just mimicking that. So that was the simplest way to derive that thing, but this is the definition of the statistics. This is the definition of the statistics, how to define in terms of the characters. Yeah, that is trivially match. That will trivially match with that thing.
Extract out the symmetry expression for the botany. Relate to I if there is only that part is symmetry for.
Yeah, exactly. So yeah, so I don't want to go there as of now because I discussed the symmetric and symmetric product when we talk about that. Yeah. So as of now, you can think of this is the definition of a statistics for the bosonic and the fermionic thing, and how this works we will come to know later. Okay. Okay, and this statistics has a very interesting property that they are additive. So in a sense that if you have a phi r chi r and then you have a phi r prime chi r prime, they actually statistics of phi r chi r. Okay, so you can see this is in the exponential, and they are just scalar functions, so they just add up. So there is no notion of commutativity, non-commutativity, because they are just the scalar functions and these are just the spurions. So it just simply multiply e to the power a times e to the power b, it's like e to the power a plus b. Next time onwards I will not allow you to enter. Just so now let's say this is for a single group, right? So now let's say it may happen, for example, standard model. Standard model, if you think a single field is transforming under multiple groups. For example, Higgs, if you think of, it has a SU2 and U1. If you think about, for example, quark doublet, they have SU3 charges, they have SU2 charges, they have U1 charges. So what is the next thing? We need to know how I can write down the plethysticks of a single field, but now transforming under multiple symmetries, right? So that's how basically your plethysticks you write down phi r1 r2, and that you can write down as exponential r equal to 1 to infinity phi r1 r2 to the power r, and then you have a chi r1 z k r, chi r2 y k r by r. So because the representation is unique, so I have only one spurion, because this spurion represents the field that is transforming under, let's say, two different groups, G1 and G2. Okay, under G1 that transforms as a R1, under G2 that transforms as a R2. So that's why the two different representations are there. But now, because these groups, when you write down the symmetries, so you assume they basically write a no semi-direct product, but a direct product form. So they are not interfering with each other. They are independent symmetries. So that's why you have to write down the character corresponding to R1 representations, and that's why the torus coordinates are different. Then when you write down the R2 representations correspond to the symmetry G2, their torus coordinates are different. Okay, so this is the combined character of a representations under a product group G1 cross G2. So these two things are different. Here we assume there's only one symmetric group, but I have a two different fields. Okay, and they have two different representations. So that's why you have two different spurions and two different characters. But more importantly, these characters are function of the same coordinates, because the group is basically unique. But now representation is only one field is there which transform under two different groups G1 and G2. That's why for each G1 I will have a maximal torus, and that corresponds to the character here ZJ coordinates. Okay, and then I will have another G2 symmetries which are parameterized by the YK coordinates. Is that 2 point clear? Because now you can see, if I have a knowledge of these two things along with this one, now you can think of writing plethysticks for any arbitrary theory. You can have any number of group, you can have any number of representations, and simultaneously you follow this rule and you can write down the characters and simultaneously write down the plethysticks. Okay? Yeah, up to this part any question? Why doesn't? What do you mean Feynman does have a character? What? Ah, okay, this one. I don't understand. Ah, this one. Ah, okay. No. Because the spurions are always hanging around along with the characters. Yeah. Okay. Any other question? Okay. Fine. So now we talk little bit of definition of the Hilbert series. So if I have this information, and let's say I have a product group so this is my product group, okay, and I'm assuming at this point all are direct product, okay, such that I can treat those coordinates to be independent. Then for this I can define my Hilbert series as phi I as j equal to 1 to n, let's say j equal to 1 to n, and then j d mu j plethystic exponential phi I r j, right? So this is the definition of the Hilbert series, that you have constructed the plethysticks and then you are actually gluing that with this Haar measure. So this is the Haar measure corresponding to the product group. Okay. For example, let's say if I have a SU2 cross SU3 theory, so I will have a d mu SU2 and d mu SU3. And as I told you, the beautiful aspect is that these are all just a scalar variables. So their positioning, whether you have to integrate first with respect to SU3 or SU2 or vice versa, it doesn't matter at all, because this is just a simple complex scalar integral. There is no notion of vector or operator here. Okay, and that's why the output, the projected invariant output that you will get is not an operator, they are more like a polynomial. Okay. Yeah. That's why I'm talking about the connected compact group. I didn't talk about the non-compact group at all. If your symmetry group is, space-time symmetry is connected, still this holds actually. So it's not about the internal symmetry. I'm talking about the connected group only, connected compact group. Okay. Yeah. Any other question? Fine. Don't complicate things. The thing is, basically I told you, if your space-time symmetry is compact, this definition still holds. Hmm.
There will be a semi-direct product. So you told this definition is true for the direct product of the segment if you have to. So when you have a point there, even if you compactify it,
Yeah.
there will be a semi-direct product, right?
Are they continuous group?
No.
Then, because all the words are important, right? Connected, compact, Lie groups I'm talking about, continuous group. So how do you write a character for a discrete group then? Okay, so then if I have, for example, let's say any function, because when you expand this, basically what you generate, it's a function of the torus coordinates. Now if you have, then you can write it down as it like Ci, chi, zz. Why? Because these are basically forming like a basis, like the representations you use as a basis. Okay, so these are more like a basis. So what we do, if I use this kind of integral form, d mu chi ij, it gives you delta ij. So because using this power of the orthonormality, you can think of like a in vector space. Let's say I have a notion about the basis vectors, okay, and then I write down any arbitrary vector in that vector space. Okay, so what I can do, I can take an inner product, okay, and then project out the components along the basis vectors. Okay, so you can think of any arbitrary complex function as a function of the torus coordinates. If I write down, okay, that I should be able to decompose in terms of the characters. Okay, because the characters are like the basis vectors, and Ci will be projected accordingly, and this Ci eventually is connected with the counting. Okay, because if the chi you can think of as a collection of the characters of different kind of thing. So I have a different characters are multiplying in the prefix automatically Ci times Cj and so on. So eventually the final counting will be related to individual this product of the Ci's in their particular combinations. Okay. So the main idea of this whole exercise is you first write down your Lie groups, compact Lie groups in terms of their maximal torus, such that you can write down the representations in terms of the torus coordinates. Okay, there's a 1-to-1 correspondence there, and similarly you can write down your Haar measure or the group space volume. Basically, you can think of that way in terms of the torus coordinates, and the tensor product of the representations you are translating in terms of as if like a scalar integral in terms of unimodular complex number. Okay, so it's just you are translating the tensor product into a unimodular complex number integral, and you are using the residue theorem to project out the invariants. And once you identify the invariants and projecting out, that is what you are actually looking for. Okay, so that is what we are actually doing, nothing more than that. Okay, so now you can understand at this point when we define the Hilbert series. So what we need to know two things: how I can construct a character function, because so far I have not explicitly computed them, I just show that okay, this is the character of some representations. But what is the character? Because if you have to perform the integral, you need to know how to calculate the character function, the explicit functions. Okay, and second, how I write down the Haar measure for a given group in terms of those coordinates. because only then I will reduce this integral into a unimodular complex variable integral, right. So our next target would be to how to calculate this guy and this guy explicitly for a given group. Okay, because this is so far is just an algebraic definitions, but with up to this knowledge we cannot really compute something. So if you have to compute something, we need to know how to explicitly compute them, and that's what we are going to learn today. Okay, any question up to this part? Okay, so let's try to recall again. So it's a complex Lie group and torus. So that is the space we are working with, and there's a mutual dependency on that thing. So a torus in a compact Lie group. Okay, when I'm saying compact, also I meant connected also. Okay, is a compact connected abelian subgroups of CLG, and it is maximal when maximal among subgroups. Okay, so eventually what we'll do, so if I talk about, let's say, SUN, okay, so what is the rank of SUN? N minus 1, okay, because you have that many commuting generators, maximum commuting generators, rank is Nn. So equivalently your maximum torus is basically Tn minus 1. So you can think of this now a product of U1 N minus 1 copies. That's how we defined. Now you can see, going back to the abelian thing, so I parameterize U1 in terms of 1z, right? So that means if you have a n minus 1 number of U1 and all are independent, so how many unimodular complex number you require? N minus 1. So Z1 to Zn minus 1, right? So that means I can think of that any representations of SUN I can write down as a complex function of n minus 1 number of unimodular complex numbers. Okay, and more importantly, the number of variable, okay, doesn't depend on the representations. This is characterized by the property of the group. That means whether you are talking about the R representations of SUN or R prime of SUN, it doesn't matter. Both will be function of n minus 1 number of the unimodular Z. Okay, but as long as I change the group, for example, if I go to SU2 to SU3, you can see the number of variable changes because the rank of the groups are different. It may happen that sometimes two groups have the same rank, but if the two groups are different, if there is no any kind of isomorphism or homomorphism between them, then even their rank is same. I mean, their variables are different. But if, let's say, for example, SU2 and SO3, their algebra is isomorphic. Okay, so in that particular case, if I write down as symmetric information in terms of SU2, or if I want to go into SO3 basis, I can parameterize this in terms of the same number of Z coordinates. Yeah. Huh? Rank, maximum number of commuting generators. Yes. So it's basically, if you look at the Cartan classification of the Lie group, okay, it defines the Cartan space. For example, SU2 rank is 1 because you have a Z3 or Z3, how do you call it? And then for SU3, you have a lambda 3 and lambda 8. But why I am calling it a maximal? Because as I told you, these are all basically bases. Like generators are basically bases in the group space, and their matrix representations are not unique. So you can go to a random arbitrary basis for SU3, let's say, where you can find out none of them are diagonal, but that doesn't mean that in that particular basis the rank of SU3 is 0. No, it doesn't work like that. So you have to find out what is the Cartan generators, how many maximum number of commuting generators you have. Because why do we emphasize that thing? Because that's how we parameterize the states. So like in quantum mechanics, when you define a state, it defines some kind of quantum numbers, like, and sometimes you may heard about something called the good quantum numbers and all those things. So these, if they're commuting generators, then I want to define my state using the eigenvalue of those generators, and that's how we define the this thing along with the Casimirs and all those things. Okay. Okay. Yeah. Any question up to this part? Fine. So now let me define the general torus and we can proceed with that. So if I talk about a unitary group UN, the torus will be Tn, because UN rank is n, so it's a Tn, right? Because when you talk about the SUN, you put an extra constant by demanding the determinant to be 1, and that's why it actually reduced by 1 this thing. So this Tn is parameterized as diagonal e to the power I theta 1, e to the power I theta 2, I theta n. Because each are basically your either in terms of the polar coordinate theta 1, theta 2, theta 3, or in terms of write down Z1, Z2, Z3. That's the unimodular parameterization you can make it. Okay. Now if I think about in terms of the SUN, so this is actually Tn minus 1, and there your Tn minus 1 is related as diagonal e to the power I theta 1, e to the power I theta 2 minus theta 1, minus I theta n minus 1. This is just from the determinant to be 1. From the criteria, I can parameterize this thing. Now, you can say if you take a determinant, basically it is a sum of the your exponential arguments, and they cancel to be 0, so you get basically 1. Okay. So this is how we parameterize the maximal torus. So now we will primarily focus on basically SUN. Okay. I'm sorry, because the size of the board is so small, so I have to remove again and again all those things. Okay. So our primary focus is basically SUN, but also we will learn how to calculate the characters and all those things for these groups. And for the symplectic group and all those things, I just mentioned. And now you can understand that what kind of assignment you are going to receive next week. Basically, calculate the hard measures and the characters, okay, for different kind of representations and the groups. Okay, so that will be the primary assignment to calculate. Okay. So now let's assume an irreducible representation M of SUN. Okay. I hope you are familiar with the language of irreducibility and all those things. If you are not, I am sorry, I cannot describe them in detail. Please go back and read. So this is the irreducible representations. Okay. So now the character correspond to this thing written as M of D of G. This is just the mathematical convention of writing. But this is still not going to help us to calculate something. This is just an abstract way of defining. So my chi D, G is written as a trace of dg. So that's why the definition of wild character, that it's a trace of the irreducible representations. And now you can see, as a physicist, just the abstract definition doesn't work for us. If I say, okay, irreducible representations trace, what does it mean? And what will you do with that thing, and how that definition will help me to calculate the Hilbert series. So still the working knowledge is not achieved. But still I want to give you the definition such that when you converse with the people, you can show off little bit rather than just doing the calculation, but that is not enough. So the next step is also important, okay, that to do the calculations. So the while character now definition is written as a Rn minus 1 m of epsilon R1 epsilon R2 epsilon Rn minus 1 1 and then epsilon n minus 1 epsilon n minus 2. Okay, so this is how you define the while character. Now what is the meaning of this numerator and denominator? Let me explain to you. So here I am using epsilon as my unimodular complex number, okay, and then we'll see how we can parameterize this thing. So where I define the ME, yeah, okay. So M epsilon is basically your diagonal epsilon 1, epsilon 2 and so to epsilon n, but yeah. Okay. So that is the irreducible representations writing in terms of the torus coordinates. Okay. But now I am calculating the character correspond to that irreducible representations, and that is written by this quantity. There is something written in the numerator, there is something written in the denominator, and I will explain what is this convention, how to write them this thing. But before going there, you can see I have write down this SUN in terms of epsilon 1 to epsilon n. So how many variables are there? N number of variables. But what is the rank? N minus 1. So automatically not all the epsilons are independent. Okay, and because they satisfy this criteria also. Product of all the epsilons equal to 1. So you can see now you have n minus 1 number of variable, because you start with the n, you put one constant, so you have n minus 1 number of variable. Okay. So now here what is this R1, R2 and all those things? They are basically integers, and such that this is the ordering of them Rn minus 1 greater than 0. Okay, yeah.
So the while bracket is something for integers.
Sorry, which one?
Representations. For this case, SPN is general.
Yes. Yes. Otherwise we can. Otherwise there is no problem with the Lorentz group thing. It's a finite dimension and unitary.
Also, like characters for usable, say, 2 plus 3. If I write a 5, then basically breaks into 5.
Yeah, we can do many things, but the point is basically as a physicist, what is the purpose of dealing with a reducible representation? Yeah, so as I told you, our target is to not develop the maths, try to solve a physics problem. So physics problem we deal with the irreducible representation. So our primary focus on that thing. So we focus on the irreducible representations, and I'll give some homework how to calculate the reducible representations on that. Okay, so now let's focus on the numerator. So the numerator, what I have written as like a epsilon R1 to up to epsilon Rn minus 1 is actually written as a epsilon 1 R1 epsilon 1 R2 epsilon 1 Rn minus 1 and then epsilon n R1 epsilon n R2 epsilon n Rn minus 1. So this is actually a very close compact form of this matrix, and this implies basically you are calculating the determinant of this matrix. Okay. So this is the definition of this thing. So now you can see at this point we do not know what is my R1, R2, R3 apart from some property of this thing. So we'll come back to that thing, how to calculate the R1, R2, R3. But at least you know, if I know the R1, R2, R3, I can always calculate the numerator. Okay. Now my denominator is epsilon n minus 1, epsilon n minus 2, epsilon 1. What's written as a epsilon 1 n minus 1, epsilon 1 n minus 2, epsilon 1 1, epsilon n minus 1, epsilon n minus 2, epsilon n. So this is my denominator. Okay. Now if I calculate, let's say, for any given SUN the denominator, okay, the question is, now if I change the representation, does the denominator changes? No, because once I fix my SUN, then the n is fixed, right? So automatically everything you know in terms of the epsilons. If I change my representations, that will not change. So this has a special name and will be very useful later. It's called a van der Monde determinant. So this denominator is actually the van der Monde determinant, and this will be, again we'll come back to this thing when we define the Haar measure. So because see, the two things you have to understand. Haar measure is a property of the group. That means the Haar measure, once you fix the group, if you change the representations, that doesn't change. Okay, but when you talk about the characters correspond to the representations. So for different representations, the characters has to be different. Now when you define this character, then you can see that the two aspects of this, one is numerator, one is the denominator, and both are written in this particular form. And if you focus on the denominator part, in the denominator part there is no information about the representations, because it is somehow immune to the dimension of the representation. It's unique for given group. So somewhere I must have a representation dependence. Where is that? In the numerator. And the numerator I have two quantities, one is epsilon, one is r. So epsilons are basically fixed for a given group like this thing. So small r, this quantity carries the information about the representations. That means the value of the r1, r2 and all those things will be different for different representations, and not only different, they will be unique for the corresponding representation. That means they are not overlap, because if you see, if they overlap, that will end up having the same character for different representations. Okay. So you can understand already that what will be our next task. The next task will be to calculate how to extract the information of small r for a given representation, and once we do that, then we are basically home, because everything we know, we put it back, we calculate the character in terms of the epsilons. Yeah.
So constraint character so those things like
Yeah, these are all mathematically constructed constant.
special reason for
Yeah, because you have a n minus 1 number of variable, and these are all unimodular, and basically when you talk about this thing, the determinant is basically 1. So the trace of the epsilon arguments, if you parameterize in the polar coordinate, the trace has to be 0. Not trace of the epsilon. If you parameterize them in terms of polar coordinate, the trace has to be 0, because that is the one constant you are imposing by the determinant. It's like a determinant. Exactly. Up to this part clear? So we should go step by step. So if we don't understand the previous step, we cannot proceed. So please, if you have any question, ask me at this point. Okay, fine. So now you can see that we have written in terms of all these things in terms of epsilons, but here, as I told you, that I have n number of epsilon. So these are not exactly the correct variable to define the character. Because why? Because the character should be function of n minus 1 number of parameter. So then what I have to do actually, I have to choose a basis like z1 to zn minus 1, where these are independent, and I have to set up a relation between this z and these epsilons. Okay, because you cannot have a extra number of parameter in your character computation which is more than your rank. So I have to go to a basis. So you can think of if this epsilon basis is like a overestimated basis. So you have to remove those dependency, okay, and to remove the dependency, then I can map that n number of epsilon to actually n minus 1 dimensional plane, okay, and that plane is basically described by n minus 1 number of unimodular this thing. And here also the same constant that each zj equal to 1. Now you see there is no this kind of relations there anymore because they are independent, but still they are unimodular because of the property of the torus coordinates. Okay, so we have to understand this correspondence epsilon I with the zj. Okay, fine. So then let's choose two bases epsilon a, where a goes from 1 to n, and then you have a zi where I goes from 1 to n minus 1. Okay, so eventually what we can say epsilon a is a function of zi. So that is the relation we have to set up, because that is the relation will give you how to realize in terms of epsilon in terms of the z coordinates. Okay, so let's try to understand this thing. So I hope all of you are familiar with this root, weight, all those things. You have done group theory, right? Group theory, quantum field theory. Yeah, very good. So then let's talk about the SUN. So what is the Dynkin diagram for SUN? The Dynkin diagram for SUN is n minus 1 number of blob. Okay, so rank is n minus 1, so it's a n minus 1 number of blob. And once you have this Dynkin diagram, automatically I can write down the Cartan matrix. So what is my Cartan matrix for SUN? 2 minus 1 minus 1 2 minus 1 minus 1 2 minus 1 minus 1 2 and so on, and all other elements are basically 0. So let me spend one line, nothing more than that. Then okay, how do you translate them? So if you know the Cartan matrix, okay, so this Cartan matrix have the information about the roots. So when you, for a given group, when you calculate the root classification, so you start with basically a paired number of roots. That means you have a n number of positive root, you have a n number of negative roots, and there's a way to define positive and negative root. And now if you focus on the positive root part, not all the positive roots are independent, linearly independent. Okay, what you can do, you find out that out of this n number of positive roots, some of the roots you can write down as a linear, positive linear combination of other roots. For example, let's say SU3, I'll have a alpha 1, alpha 2, alpha 3, and then I may get alpha 1 plus alpha 2. So then you can see that one of the root is basically linearly dependent on other two. So I have to find out what are the linearly independent positive roots. Okay, so linearly independent positive roots, which call the simple roots. Okay, and those I am calling as an alpha I. Now how many simple roots will be there for a given group? If my rank of the group is n, I will have a n number of simple roots. So now SUN, my rank is n minus 1, so I will have a n minus 1 number of simple roots. Okay, and then what you can do, if you calculate the matrix element alpha I alpha j over alpha j alpha j. So this is what the definition of the matrix element of the Cartan matrix. So if I know the positive root, I can take an inner product in a very similar sense as like you do the in quantum mechanics in the linear vector space, those kind of theories, you take these and you calculate for SUN and you exactly get this matrix. Okay. Sorry, there's a 2 factor here. Yeah. That's for the normalizations. And now you can see for I equal to j, it is basically 2. That's why all the diagonal elements are 2. Okay. And which simple root doesn't have any kind of connection. That means basically they are basically inner product is 0 because they are orthogonal to each other. Okay. And that tells you basically why these elements are basically 0. So the -1 will come out with only those simple roots which have an angle between them. Okay. But there are some simple roots which are orthogonal to others, they will give you 0, and that is the origin of this 0. But please, if you are not familiar with this thing, please read before the next class, because I cannot go further detail about this thing. So now once you have this Cartan matrix, okay, then you for every 2 you draw one blob, okay, and then you find out between these 2 blob what is the maximum number of handles in the off diagonal entries. For example, in this particular case, this is 1. Okay, both are 1. So that's why they are connected by 1. But this is more like a cascade kind of thing, because all the off diagonal elements corresponding are there. So you can think of it like a 1-dimensional lattice. So n and n minus 1 is connected to each other, or the n plus 1. There's no other handle. But this is certainly not true when you talk about groups like SO2n, SO2n plus 1, or symplectic group, or XSNN groups. They are different. So I'll come back to this thing when I'll try to calculate the character for them. But for SUN, this is the very simplest one, and that's how the correspondence between the Dynkin diagram and the Cartan matrix you set up. Okay, fine. So now, So again, this root system form kind of a basis. So I can go and choose a particular basis for that thing. So here my basis will be like this: alpha 1, alpha 2, and alpha n minus 1. So where alpha 1 is nothing but my first row, alpha 2 is nothing but my second row, and so on. So I have a Cartan matrix. I define the alpha 1, alpha 2, alpha n minus 1, and alpha 1 is like an array vector of the first row, alpha 2 is the array vector corresponding to the second row, and so on. So that's how you read this alpha 1 to alpha n minus 1 from the Cartan matrix. Okay, so you know the Dynkin diagram. From the Dynkin diagram, you directly write down the Cartan matrix. Once you write down the Cartan matrix, you identify the alpha n's. That's how the flowchart goes. Okay, fine. So now, for any given group, for the representation theory, we primarily focus on. Okay, I'll come back to this. So I'll start with the fundamental representations. Okay. So what is the definition of fundamental representations? Anyone who are crediting the course? Are you familiar with the fundamental representations? What is the meaning of fundamental representation? And how many fundamental representations I have for a given group? Nope. That's why I asked the question. I know this is the answer. For SU2, it's a very simple. Even the wrong answer become correct. No, that's what I'm saying. Even for SU2, the wrong answer falls correct. Think about any arbitrary group. For SU3, how many fundamental representations are there? For SU4, how many fundamental representations are there? Yep. Okay. For SUN, I have n minus 1 number of fundamental representations. So after these lectures, you will understand that you think you know group theory, but you don't know group theory. So for SUN, you have an n minus 1 number of fundamental representations. Okay, and then the definition of a fundamental representation is by Dynkin level. 0 A1, 1 A2, 0 A3 with A1 plus A2 plus A3 equal to n minus 1. So that's the definition of fundamental representation. So you write down the Dynkin level. Okay, so you can see if I have, let's say, SU3. For SU2 is a trivial, that's what I said. For every wrong answer false correct in for SU2. SU2 you have a 1, but it coincidentally correct. But for SU3 you have a 2. What are those? 3 and 3 bar. fundamental and anti-fundamental representation, because anti-fundamental is also fundamental. But for SU4, it's more non-trivial. You have a 3. What are those? 4, 4 bar and 6. Now, what you know in your mind as a fundamental representation, that is called the lowest dimensional fundamental representations. So lowest dimensional fundamental is 1, because lowest can be only 1, right? Yeah. So now, for example, if I have a, now you can see, let me give you one example for SU3. So SU3, I can have a 0, 1 and 1, 0, right? For SU4, I have 0, 0, 1, I have a 0, 1, 0 and 1, 0, 0. And at this point you may think that okay, there's only 1 in each such Dynkin level. Why the dimensions are different? Because there is an asymmetry. So if you call it, let's say A1, A2, A3, that's how the element. If you calculate, there is a fantastic relation between the calculating the dimension from the Dynkin level of the representations. That is not symmetric under A1, A2, A3. Some of the elements are biased. I mean, the A2 comes with more weight factor compared to A1, A3. So what you will find out that this and this are basically having the same dimension, but this will have a different dimension. This is the 6. So this is the 4. So this is the 4. This is the 4 bar, and this is the 6. Okay. So I'll give you as a homework to calculate the dimension from the Dynkin level, so that you can brush up your result. Okay. Fine. So now, among those fundamental representations, I will focus on the lowest dimensional fundamental representation. Lowest dimensional fundamental representation is this one. That the first element in the Dynkin level is 1, others are 0. So that is the definition of my LDF. So the definition of LDF is 1, 0, 0. Zero to the 0, A1 times 0, you can have A2.
Like this, 0, 0.
Yeah, exactly. How many times you shift that thing?
So can you not have 1, 1, 0?
Yeah, but they are not the fundamental representations.
The fundamental representations are the ones where
Somewhere. So you can have more than, so these are more like a position.
but A2 here.
Yeah, so that's what I'm saying. It's not like A to the power x. It's a position.
Yeah.
Okay. That means basically at the fundamental representation, out of this, for example, SUN, you have n minus 1 number of entry. Okay. You can have only one entry non-zero. All other elements are basically 0. Okay. Now, if I entered more 1 there, they are basically my higher dimensional representations. For example, if I 1, 0, 1 or 0, 1, 1, they are the higher dimensional representation. They are not the fundamental. For the fundamental, only one element is 1, all other 0. Now, where do you place the 1? That many possibilities will give you basically by the rank. Okay. But still, as I told you that even this array has only 1, 1, this also 1, this also 1, but because the dimension depends on the position of the 1. Okay, that's why the dimension of this Dynkin level is different than this and this, and that you can see by looking to the how do you write down the dimension in terms of the Dynkin level.
I don't think we did it.
Yeah, I also think so. That's why, but we cannot help each other unless you just read that up, and you can, if you have some query, but please feel free. But before you read, okay, yeah, but because you can see I cannot go and diverge that direction, but at least I am giving the glimpse of this thing. Yeah. Okay, so this is now I am working with the lowest dimensional fundamental representations. This is unique because that's why I say lowest, and that Dynkin level is always for SUN minus SUN. Is first element is 1, all other elements are basically 0. So that's why I have a n minus 2 number of elements are basically 0. So this is my lowest dimensional fundamental representations. Very good. So now I'll calculate something called the weight tree. But where do I calculate? Okay, let me remove this part then. Yes. Now something I will calculate the weight tree. Okay. So how do I calculate weight tree? So what I'll do, I'll start with a LDF. Okay. and I'll subtract alpha 1, alpha 2, alpha 3 continuously, as many as I can. So now let me call the first one as 1, 0, okay, and then my L2 is L1 minus alpha 1. So this will be like a minus 1, 1, 0. Then I have a L3, I'll define as a L2 minus alpha 2, and so on. So my Ln will be Ln minus 1 minus alpha n minus 1. Okay. So what I'm doing, so I start with this, and then that I define as L1. My L2 is basically L1 minus alpha 1. Alpha 1 is this row vector. Okay. And then I get my L2. So then I calculate the L3 by subtracting alpha 2, the next row, from the L2, and that's how I get a basically tower. Okay, and this tower is called the weight tree. And why I'm calculating this weight tree, I'll come to that. So but this is eventually read up minus 1. So once you reach here, you know there is no other way you can subtract them. It's just a one way of subtraction. Okay. And this also, okay, so I don't want to go to the group theory more, which is relevant only. Otherwise, I can explain what is the meaning of this starting 1 and then the last element, the minus 1, because they are the conjugate of each other. Okay, fine. So now the generic, now the generic definition, the generic definition of n minus 1 tuple Li is basically Li as small li1, small li2, small li to the power n minus 1. So this is the generic definition of my Li. And once I identify them, then I can write it down as a epsilon I as my z1 to the power li1 times z2 to the power li2 times zn minus 1 to the power lin minus 1. Okay. So first I calculate the weight tree, and once I calculate the weight tree, so I know basically for any Li, I mean ith element here, what are the entries for this thing, because these quantities are known to me. For example, if I take a L1, my Li1 is 1, all other Li's are basically 0, Li2 and all those things. So I stands for which capital Li you are talking about, and these 1, 2, 3 stands for in which position in that array vector. Okay. So from the weight tree I have information about everything, small li and the capital Li, everything, and then I have this kind of relation. Okay. So I will not go to prove why, how this relation holds and all those things. This is just a, you can think of as a given. This is the way we can relate basically epsilons and the z's, and that's how I can now calculate all the relations. Epsilon 1 is basically my z1, epsilon 2 will be z1 inverse, z2 and so on, and epsilon n would be my zn minus 1 inverse. And this is very, though we solve this thing algebraically, but if you try to recall how do we write down the torus coordinate for the SUN Tn minus 1, it was e to the power I theta 1, then e to the power I theta 2 minus theta 1. So now if e to the power I theta 1, if you think of like a z1, so first element is basically my z1, then it was like a z1 inverse z2, because this is e to minus I theta 1, and now if you take the product of them, you will see they will exactly all the z's are cancelled, and you basically get the 1 which was written somewhere here. Okay, so this is one way to be consistent. Try to recall this one, this structure, diagonal e to the power I theta 1, e to the power I theta 2 minus theta 1, and so on. So that's one way to algebraically get that structure, how these epsilons are related to my these torus coordinates. Okay. Yeah, so small li is basically the element of the, let's say, let's talk about the L2, which is non-trivial. Okay, so for L2, a small L21 is -1, small L22 is basically 1, all other small is basically 0. You map that thing. Exactly. So like an array vector, and in the entries you just computing them. Yeah.
How do you know when you reach the last stage?
Hmm?
The lowest stage possible. These L1 and the next stage, right?
Hmm.
We go on.
Yeah. So basically, what happens? So when you calculate the weight tree, okay, then you will find out the number of element in that weight tree. Okay, is basically the dimensionality of that state. Okay, and then that Dynkin level correspond to within this component of those multiplet. If you think of, okay, they're always like a conjugate way of doing that. Conjugate in, okay, you define a conjugation that if you start with 1 0 0, you will end up in the weight tree always as a 0 0 0 all -1, because then you cannot subtract more than that. Yes, because you do not have any further alpha. You have exhausted all the alphas. Exactly. So that's it's a monotonically you go downwards. No. Yes. So you have to subtract alpha 1 and then alpha 2, then alpha 3 and so on. Otherwise you will mess up actually. Yeah. Now the reason is basically alpha 1 and alpha 2 are not very independent way in this whole construction, because alpha 1 is linked with the alpha 2. Alpha 1 is not linked with the alpha 3. So if you subtract alpha 3 instead of alpha 2, then you are making wrong. Yeah, that is a different thing. So, okay. Any other question? Fine. So we have set up the relation between the epsilons and the z's. Now what is left? We have to come back to calculate the small r. Okay. So let's see how to calculate the small r. Maybe I can subtract this one. Okay, so let's assume a representation in the Dynkin level form as if like a1, a2, an minus 1. So this is the Dynkin level of some arbitrary representations R. I do not know what is that representation. Okay. Now for that given representation, we need to calculate the small r. Okay. But before proceeding, any further question? Okay. So then, what we can write down, this as I told you that any representations are always in a tensor product. If you try to recall that we start with the fundamental representations, because fundamental representations form like a basis of the constructing of the higher dimensional representations. If I have the information about the fundamental representations, I can construct all other higher dimensional representations. Okay, so that's why in this kind of analysis, I can use the weight tree of the lowest dimensional fundamental representations as if like a basis of any arbitrary representations. That means this is the arbitrary Dynkin level for a given representation R. This I can write down using the weight tree of this thing, because each such L1 are like my basis. So this I can write down as a lambda 1, 1, 0, 0 plus lambda 2 minus 1, 1, 0 plus so on, and then lambda n 0 minus 1. And when that means it's like a representation point from the Dynkin space, I am writing the Dynkin level in terms of basis of a lowest dimensional fundamental weight tree. And lambda 1, lambda 2, lambda 3 are like my weights, like Similarly, as a vector space, you write down an arbitrary vector as like a Ci, Ci are basically like the finding that probability of something like that. It's like a weight factor there. Okay. So similarly, these lambdas are attached with this thing. So what you do, we have to solve for this lambda. So this is a homework I am putting because this is just an algebra. But arbitrary lambda k you can write down in this following form: I equal to 1 to n minus 1 ai minus j equal to 1 to k minus 1 aj. Okay. So this is, yeah. Okay. So we can invert this relation and we can express my lambdas in terms of the age. And if I do that, then I know what is my r. Then I can write down r vector as my lambda vector plus rho vector, where my rho I is basically n minus I. So you can see if I start with this r is related to this lambda plus rho, but rho vector, writing the rho vector is very simple because it is independent of the representations. If I know my SUN, then I know rho 1 will be n minus 1, then n minus 2, and up to rho n will be 0. Right? And it's independent representations. Then I have to calculate lambda, and lambda is the quantity which contains the information of the representations. And through this lambda, the dependency of the representations in R actually gets injected. So that's how I calculate my small r. Okay. And now you see, if you go back to the character formula, I know what is my R1, R2, R3, everything. Because when what I'm giving to you, I'm giving you the symmetry and the representations in terms of the fields. When I say the representations, automatically I know what is my A1, A2, A3. So all these information are like an input in this whole prescription. If I know my A1, A2, A3, I know all my lambda. If I know all my lambda and I know my group, so I know my rho, I can calculate my R. And if I know my R, I plug it back in terms of epsilon. So I calculate the character in terms of my epsilon. And then I know how my epsilon is related to Z. I replace that variable, I get my character in terms of the Z. Okay? Yeah. No. Please, bro. Which one? Rho. Rho is basically, rho 1 is n minus 1, n minus 2, and so on.
So I should have a increase in the.
Yeah, all are vectors. So rho I is the ith element in that vector.
So say n minus 1.
Yeah. So let's say SU3. So the SU3, the rho 1 would be 2, then that rho 2 will be 1, rho 3 will be 0. No, 0, 3. Rho 1, rho 2, rho 3. For SU3, rho 1 is 3 minus 1 equal to 2, rho 2 equal to 3 minus 2 equal to 1, rho 3 equal to 3 minus 3 equal to 0. So my rho vector is rho 1, rho 2, rho 3. Because it has to add with the lambda 1, lambda 3 to give you R1, R2, R3. So positions are important. Okay?
So basically we are doing for SUN. So I think for other groups, like other groups, the definition of epsilon I is what will be the same.
No, this is for the SUN, the epsilon to Z. The other group, the advantage basically I don't need to change epsilon to Z. Those epsilons are inbuilt having the similar property as the Z. This is very specific to the SUN. The reason is basically, let me give you one example. I'll come back to this thing later. If you think about the SO2N group, so SO2N, the torus is basically, it's a 2 by 2 SO2, right? All are basically cos theta, sin theta, minus sin theta. Once I diagonalize them, I can add e to the power minus I theta 1, e to the power I theta 1. So in that particular pairing form is already there, epsilon 1 inverse. So I don't need to worry about going back there.
But then this definition for R and given that
That will be same.
that will be same.
Yeah.
this n, because you need to define no vector.
Yeah.
It's defined as n minus I. So will this definition will be defined as like this is n for SU1. Suppose I have some u1.
Yeah. So we'll define the row for the SO2n. Yes, 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 yeah. Yes. Okay, but yeah. So whatever we are discussing at this point, let's keep in mind for the SU1 and what are the generalizations you have to make, we'll comment on that thing. Okay. Okay. But yeah, up to this part, any question? Now that's a very interesting, way to calculate lambda from the Young diagram also. Let me give you a hint, but that is not for the calculation purpose, just for a different interpretation. Okay. I think this thing. So let's say for SUN, I draw this kind of some arbitrary 1, 2, 3, 4. So it's like a 1, 2, 3, 4, 5, and then I draw this one. Oh. So lambda 1, lambda 2, lambda 3, lambda 4. So for any non-trivial representations apart from identity, because why I am not calling it identity, because identity is very trivial representations, and for SUN, by the way, do you know for SUN how do you represent a singlet in a Young diagram? Only credit. Who are doing the credits, not the audit ones. The part of the marks grading may. You have not done the Young diagram? But if you stay only in the fundamental representations, you cannot proceed in life. You have to create the hard dimensional representations also. So the thumb rule basically for SUN, if you have n number of vertical boxes, that's a singlet. How to define the anti-fundamental representations? Anti-fundamental row. It's a recording, otherwise I would give the answer. So the n minus 1 number of vertical boxes is the n bar. Okay, and n for SUN, which is the lowest dimensional fundamental representations, is basically the single box n. But that's the lowest dimensional fundamental representations. Okay. Now if you go horizontally, you get all the symmetric states, and all the basically vertically you have anti-symmetric states correspondingly. Yeah, so brush up your group theory, man. Very poor condition. So now lambdas, if you identify and calculate, then you see for that particular representations my Young diagram is unique. Right? I can have a representation and I can have a Young diagram for that, right? And then you can identify that lambda 1 is nothing but the number of boxes in the first row, lambda 2 is nothing but the boxes in the second row, and so on. And that's how you can see that lambda n is always 0 for non-trivial representations, because if you put that box, then automatically that will be singlet and that will be removed. Okay. So that's how you can realize. So you can cross check by, for example, in this way, and then for given representations you just try to draw the Young diagram and you can cross validate that, okay, how do you realize the lambdas in this particular context. Okay, fine, good. We have till 20 minutes time to grill. Let's see. So okay, so now we'll explicitly calculate for SU2 some of the characters. Let's talk about the SU2. So for SU2, what is my epsilon 1? Z1, and epsilon 2 is Z1 inverse. Right? So what is the Dynkin level for 2? How many fundamental representations I have for SU2? 1. So what is the Dynkin level? 1. Because there is no room for 0 and I have only 1, right? Yeah. Good. And so what is my weight tree? How do you calculate the weight tree for SU2? What is my Dynkin level? This? Sorry, Dynkin diagram. What is the corresponding Cartan matrix? 1 by 1 element. So my L1 is 1, L2 is 1 minus 2 minus 1. So you get 0 and 0 inverse. Simple, na? Okay, very good. So now, what is my van der Monde determinant? Epsilon 1 to the power 1, because n minus 1. I hope you have the definition. Epsilon 1 to the power n minus 1. So that's why epsilon 1, and then it's a epsilon 2 to the power 1, 1. If you calculate, this will give you Z1 1, Z1 inverse 1, and then you get basically Z1 minus Z1 inverse. Okay. So I calculate this thing. So let me cross check for the singlet, which is a trivial one, but it's good to check always. Singlet representation is 1. What is the Dynkin level for this? 1? 0. Because it doesn't have any dimension, so all the elements are basically 0. For SUN, your singlet represented by n minus 1 number of 0. And Young diagram like this, and that's why I said non-trivial representation, because in this particular context lambda n is not equal to 0. Okay. But now, so your lambda vector is basically 1 comma 1. Your rho vector is basically 1 comma 0, because SU2. So this is fixed for SU2, independent of the representations, right? So then your R vector is basically lambda vector plus rho vector, which is 2 comma 1. Do you agree, all of you? Just vector addition. Nothing serious mathematics is going on here. Okay, now, so then my character for a singlet representation is epsilon square, epsilon 1 divided by the van der Monde determinant, and if you calculate, this will be 1. So the character for a singlet representation is just 1. Okay. Now let's calculate something non-trivial. Yeah. Let's calculate R equal to 2-dimensional representation. So it is same as the 2 bar because the pseudo representations, and that is reflected in the Young diagram also, because both the equivalent Young diagram is replaced by this. Okay. So lambda is basically 1 comma 0, because I am not calculating directly in this particular format, because this is what you are supposed to do. I am giving you the Dynkin. Okay, so I can give you the Dynkin level for this actually. Yeah, it's a 1 Dynkin level. Okay, and then use this information. Okay, so your job is to basically use this trajectory to replicate what I am writing actually. That's a nice cross check of your understanding. And then again my rho vectors remain unchanged, so this is the thing. So my R vector would be 2 comma 0. So the chi2 will be 1 by delta epsilon square fn to the power 0, or you can think of just like a 1. Okay, and I am not calculating the determinant, so it will be Z1 plus Z1 inverse. You know, calculate how to determine a matrix 2 by 2 or 3 by 3 matrix, right? Can you? Good. So I am not doing this determinant, so you can calculate the determinant. So you get Z1 plus Z1 inverse. Okay. So now let me try to calculate the character for the adjoint representations. Okay. So here my R is equal to 3, and this is the Dynkin diagram for that. I may draw sometime the wrong Dynkin diagram, you have to be careful. Is it correct Dynkin diagram for SU2 adjoint? sorry, Young diagram. Correct? नीचे आ जाएगा, नीचे तो 1 हो जाएगा. This is 1. This is 1 because SU2. So 2 vertical boxes is a singlet. So I don't need to even compute. This is 2, 3. So 6 by 2, 3. Okay. So now if this is, I want to calculate the character, but as I told you, the character formalism that I am using that replicate all the properties and all the results that I have using the representation theory, tensor product and all those things. So then from the tensor product, how do we construct the 3? 2 cross 2 equal to 3 plus 1, right? So then this is the result from the tensor product I know, 2 cross 2 equal to 3 plus 1. So I can write down equivalently 2 cross 2 minus 1 equivalently. So what does it mean? That means if the character replicates all these properties, what I supposed to get? I supposed to get chi3 should be chi2 times chi2 minus 1, because 1 is the, okay, this is a bad mathematics, so I should avoid writing this. Yeah. So the character of the one singlet representation is basically 1. Okay. So this is the character, and I know the character of SU2 2-dimensional. So and 2 bar have the same character. So if I take these 2 characters scalar, because these are the scalar variables, I don't care about, right? I multiply them and subtract 1. The tensor product tell me this should be the character. So let me calculate the character. So z1 plus z1 inverse whole square minus 1. So z1 square plus 1 by z1 square plus 1. Right? Now let's try to recalculate this using the character formalism, because this is what I am expecting if the character and the tensor product, all those things truly holds each other's hand, right? So let's try to recalculate this thing now. So then for this my lambda is basically 2 comma 0, and then rho is basically my 1 comma 0. So r is 3 comma 0, and my chi3 would be epsilon cube 1 divided by delta of E. And if you calculate in terms of z, you exactly get z1 square plus 1 by z1 square plus 1. So that's a beautiful match. So now you can see that character formalism is actually replicating the properties what we know and what we have achieved using the representation theory also, using the tensor product and so on. So they also simultaneously hold here. Okay, so now you can make a very nice cross check. For example, let's say 2 cross 3 is 4 plus 2, right? So you know the character of 3-dimensional representation and 2-dimensional representation both. So you can calculate the character for chi4 using this, okay, and then you can store that thing. And what you can do from this side, that you multiply the character of 2-dimensional representation with the 3-dimensional representation, and from that product you subtract the character of 2-dimensional representation, and what you get, that should match with the chi4. So that's a very nice cross check you can make, and you can convince yourself more and more, and that will give you better understanding. Okay, so next time, so what is the time? So we have 10 minutes. Okay. No, I think today is enough, because already I can see gray eyes, sleepy eyes. So yeah, so you do try to convince yourself through this calculation. Okay. Next day what I'll do, I'll calculate the SU3 part, because that is slightly non-trivial. You have a more 2-dimensional vectors are there. Okay, and then with the SU2, I'll try to I'll start basically this space-time symmetry information, because that requires more non-trivial mathematics there, understanding the conformal groups and all those things from that side. Okay, Yeah, but before the next class, please revise whatever been taught till today. Otherwise, there will be gap. Okay.